In the second part of this presentation, I'm going to talk about the non-contact transition scenarios. So we can, as a human, transfer our knowledge to the robots. So how we can show to the robots to do different type of motions and how they can move from one point to another point. Let's imagine one very simple example. We want to wipe a table. What we want to do, we wanted to have the robot go into the table, slide on the table, and leave the table at another point. So what we do, we have started to define the desired contact point, desired leaving point, and we have started to have a lot of demonstrations as we had before. So we showed the robot how the robot can go into this contact point, slide on the table, and leave another point. And we use one of the approaches we saw before to learn this dynamical system. So we learn the dynamical system. We're gonna have the learned dynamical system. It's gonna be FX. And what we expect to happen, we expect the robot go into the table, stay on the table, move on the table, and leave the table at another position. But it's not going to happen in reality because we have not seen the interaction forces between the robots and the table while we are demonstrating to the robot the desired task. The robot is going to have such behavior. So it goes to the table at the desired location because it has learned that, but at the desired location, it's not going to have the desired velocity. So robots start to bounce on a table. That's why we needed to modulate the dynamical system. We need to modulate this learned dynamical system such that we can make sure that the robot can go into the table in a stable manner, not only in the position, but also in velocity and from the force. So that is our objective. The robot should go into the table, stays on the table, move on the table, and leave another point. So we need to make sure that the contact is going to be stable. And a stable contact means that the robot should not bounce off the table after the impact. So impact should happen only one time. After that, the robot should go into the table at the desired location and leave the table at another location. What we assume that the table is a planar, is non-penetrable, and is passive and flat. And we assume that the contact is going to be inelastic. Inelastic contact means that the table and the robot are going to absorb a little bit the impact energy. Means that if the velocity of the robot at the impact is less than something, the robot is going to stay at impact because all the kinetic energy of the robot is going to be absorbed by the table. And just like before, we defined the desired contact point and the desired leaving point, and we assume that there is a gamma function which gives us the notion between the position of the end effector of the robot. Talk a little bit about this gamma function. We have the surface, and we define the gamma function such that if we are far from the surface, gamma function should be positive. On the surface, it should be 0, and if we are inside of the surface, it's going to be less than 0. What we have started to draw a line and say that if we are really far from the surface, we really don't need to take care of the impact force because it's not going to happen in close future. And if we are really inside of this transition, so we define the line, and after that we say that this is gonna be Fourier space motion where we don't need to take care of the impact because it's not going to happen in close future. And if we are less than rho, the impact is going to happen at any moment. So we assume there's gonna be a transition region where we need to start to modulate the motion of the robot such that it prepares itself for a contact. So we divide the space in three space: Fourier space motion, transition region, and the contact region. Based on this definition, we can say that the contact position, because it is on a contact surface, the value of the gamma function in the contact position is going to be 0. What we start to do, this was very simple definition of the transition region. We transition region by using, for example, one of the kernel approaches such that it can modulate around the desired living position, such that we can, in the desired living position, the value of the gamma function should be equal to rho. And here alpha is going to define this aperture, and we are going to play with these two open parameters, alpha and rho, in the exercise session. And you will see the effect of these two parameters on the. So how we do? We define the modulation function just like what we have seen before, and we define our dynamical system in second order because we want to control for the velocity of the robot. This modulation function should have two different properties. We should be able to directionally modulate the motion of the robot, which means that we define m function something like this to each other, or to normal to each other. It's Q1 and Q2, for example. Q1 is going to be a normal of the surface, and Q2 in this example is going to be tangential on the. And as I mentioned before, because the modulation function should not be activated if we are very far from the surface, this modulation function means that it's going to be activated only locally. It means that if we are in the Fourier space motion, this gamma, this lambda should be equal to I, means that the robot should be driven by using the nominal dynamical system, which we have learned from the demonstrations. But once we are really close to the surface, we should start to modulate the motion of the robot, and this gamma function, lambda function should be. So right now we know what is the Q and what is the lambda, but we don't know what is this small lambdas. In order to control for the impact velocity and in order to control for the impact point, we define the lambdas like this. I know they look a little bit complicated, but if we plug in this equation inside of simple equation, it's gonna be a very nice decoupled motion of the robot in each direction, and each of them is a second order dynamical system, very simple damper squared, critically damper squared dynamical system. Let's look at the motion of the robot generated in the normal direction. By studying the behavior of this dynamical system, we can say that the robot goes into the contact surface with zero velocity, and zero velocity means that the velocity of the robot is going to be less than what we expect it to be, means that the robot is going to stay on the contact. So we can make sure that the contact is going to be stable. In order to make sure that the robot goes into the contact at the desired location, we have studied the other directions, and in the other directions we can see that the motion of the robot is asymptotically converging to the x star. So what we do, we just simply say that if the robot is not on the contact surface, x star should be desired contact point. So the robot, if it is transition region, the robot should converge to the desired contact point. And if the robot is already on the contact surface, what we do, we start to change the x star. It's just very simple switching, such that the robot converges to this. How does it happen? This value is going to have this representation. Once the robot is on the contact surface, the robot starts to move from the desired contact point towards this virtual target. The robot always passes the living position between these 2 points. And at that position, as I mentioned before, we define the gamma function, we define the lambda function such that it's here. We're going to be in Fourier space motion, means that the robot should be driven by the desired and learn on target, means that it's going to leave the surface. So if we don't modulate the motion of the robot, as I mentioned before, what is going to happen? The robot is going to bounce on the surface, and you can see this is the result. Motion of the robot, we can see that we can change the velocity of the robot, and changing the velocity of the robot means that we are going to change the kinematic energy of the robot, and that changes the impact forces. And as you can see in this example, with different contact surfaces, we can make sure that the impact is going to be stable and the robot is not going to bounce off the surface after the impact. Dynamical system is great because it's very fast to compute it. And because it is very fast to compute it, we can indirectly compensate for perturbations. As you can see here, I am perturbing the robot while it's trying to execute the task. And as you can see, the robot first is compliant to me. And second, the dynamical system can compensate for this type of perturbations because at each step, it has started to look at the new position of the robot. And even though under the perturbation, it can accomplish the task, the perturbation can be on the robot side, or it can be on the object side. Even though we assume that the object is going to be is going to not to move, but as you can see, because it can compensate for this type of perturbations, we can even move the object during the task. So, any question? Sure.
My question: do you measure the position between the end effector and the surface?
Exactly.
This is accessible.
Yeah. So I have this position of the robot. I know where the surface is, and based on this, I can calculate that lambda function.
And you as well measure the force, the contact force.
No, I don't measure the force. So it's just the velocity of the robot, which matters. So if you don't have any question, we can go to the exercise session and play with the parameters, open parameters, and see how they. Oh, we have one question.
As I see your modulation, use the state, but the position of the surface. Yes. Have you tried to use or try to analyze, for example, the sensitivity of your approach to the error in the surface position?
We are studied on the paper exactly. We have studied the sensitivity of the modulation function with respect to the uncertainties. We show that we can compensate for the perturbation. We can compensate for this type of uncertainties for sure. But with this uncertainty should be bounded. We cannot, and we should know the upper bound of this uncertainty. So we can go to the exercise session.